the numbers which are not in this set, which are not quadratic residues and are quadratic non-residues. The quadratic residuosity assumption, QRA, states that it is difficult, it is computationally hard to decide whether a number, a given number with n bits is a QR or a QNR if the factorization is not known. And the number is situated in this Zn plus 1 set. This is a restriction of the set of Zn. I will not go into details because we don't really need these details. All we need to know is that there are two essential properties. If we multiply two QR numbers, we obtain a QR. So a QR times a QR is a QR. A QR multiplied with a QNR is a QNR. So this is what we need to know for the protocol. What about if we multiply a QNR with a QNR? What happens? What are we going to get? A square? Any other opinions? Sometimes. Sometimes we get a square, sometimes not, right? So the answer is maybe. Sometimes we get a QR, sometimes we get a QNR. But fortunately, we don't use this in the protocol ever, so we don't have to worry, because we're only going to use these two operations, right? So how does the protocol work for binary data? We have again the X string. This is stored at the server, right? We organize the data into a rectangular matrix. So it's the same data that we had previously, right? Each element is a bit. Now, some client wants to retrieve, let's say, the value of x10. The client will also know the geometry of the matrix. He knows how many columns and rows are. So he can determine the row and the column, right? Row is A equals to 2 and B equals to 3. Indices here start from 1. What is the user going to do? He's going to generate the query that we have seen. And this query is an array of numbers, y. Each y number is an n-bit number, right? Is a large number. Out of these numbers, we randomly generated, we make sure that y3 is a QNR. All the rest are quadratic residues. This query is sent to the server. Because the server does not know the factorization, he doesn't know which one of the numbers is a QNR and which one is a QR, right? What is the server going to do? For each row of the database of the matrix, it will multiply those y numbers for which the corresponding x value is 1. Okay? So it's some sort of a masked, if you like, a masked product. Only those elements in y which correspond to 1 values in the matrix are multiplied, right? So at the end of this protocol, each z value will store the products of the y value corresponding to the ones in the matrix. This is captured here with this complicated and useless formula. Now, what we need to know is that if the value of all these results are sent back to the user, right? We have Z1 to Z4. Why do we need to send them all? Because the server does not know in which row the element searched was in. So we have to send all this back to the user. The user will look at the value of Z2 and decide if Z2 is a QNR, then X10 must have been 1. If Z2 is a QR, then it must have been 0. Is it clear why? So the intuition is the following. The only way I could have obtained a QNR is if Y3 is included in the product, right? We have seen earlier that if I multiply 2 QRs, I only get QR. So the only way for this Z to have been to be a QNR is if Y3 was included in the product. And Y3 is included in the product for the corresponding row only if X10 would have been 1, right? Questions? Okay. So there are a few things here to highlight. First, we have some sort of redundancy in the result that is being sent. We have seen that we had that redundancy for spatial method as well. We will see how to make use of this redundancy. Second, this works for binary data. However, if we want to have objects which consist of multiple bits, we can simply imagine that we have another dimension, right? Orthogonal to the board, a depth of this matrix. And the object, the multi-bit object, will be stored in this depth, right? So what's going to happen is that instead of using the operation on bits, as we did in this protocol, we can simply have a protocol which works at the level of memory words, if you like. This is maybe a good comparison. So when we operate with memory words, we perform the operation on each bit, right? So this would be how the method works for multiple bits. Now, this is the generic PIR protocol. Now I will show how we apply this to our problem. First, I will consider approximate queries, approximate nearest neighbor queries. We have here a number of points of interest. So from this point forward, all the points that we will have in the diagrams are points of interest. There are no other users, right? There are no index, no locations of users known. The server does not know location of users. So these are the points of interest. And the idea is the following. Based on this data set of locations, we built a spatial index. This spatial index can be anything ranging from a KD tree, maybe a code tree, or code tree is unlikely, an R tree is more likely. With the following properties. In each leaf node, we must have at most square root of n elements, where n is the number of POIs. And the other condition is that the tree must have two levels. And it is easy to show that no matter what structure we use, some broad tree that we use, we can achieve these conditions. For instance, here we have a KD tree. The idea behind the KD tree is to split the space recursively until in each partition we have a limited number of users. So for instance, here we have first a split along the one axis, which gives us a partition of 3 and a large partition of 6, which is further partitioned into B and C, each of them having 3 points. This is done one time. This is a pre-processing of the data set. What happens when the user issues a query? Okay, one more step, which is important. So based on this data index, how do we build the PIR matrix that we have seen earlier? Simply by storing each leaf node into a column, right? And because of the cardinality condition, we can always do this. So the P1, P2, P1, P2, P3 leaf node will be stored in this column, right? Similarly for the other leaf nodes. When a user issues a query, first the user will retrieve the root node. This can be accessed in plain text. We don't need any encryption, right? Why is that? The root node corresponds to the entire space, right? So no matter where I am, I would still ask for the root node. So this is a protocol which is performed by every user in the system. So based on the fact that I ask the root node as a user, I don't give away any information, right? Because all the users do the same. Once I find out what the root node is, so basically I would know the rectangles A, B, and C, I will see where I am myself. And let's assume that I am in leaf C. Then what I will do, I will perform a protocol, a private information retrieval protocol, only for this column here. And this time, I will use all of the elements that I retrieved. And this is why I said that we can make use of this redundancy. So what we will do, we will bring all the elements in leaf C, P1, P2, and P3. And then the user can choose which one is the nearest. Of course, this is still approximate. If the user, for instance, would be situated somewhere around here, most likely the nearest neighbor will be P6 or P7. However, this gives good result in practice. Questions so far? Yes? First of all, there are no ASRs here. So ASRs, when we talk about ASRs, we talk about minimum boundary rectangles of users. This is just a simple partitioning and indexing of a set of points of interest. No, this is exactly what I was pointing out. There are no users here. But it's good that you pointed this out. So there are no users here. All these points here are points of interest. In our method, we do not